So last time we started talking about the spectra of angle modulated signals. To make things simple, we will consider sinusoidal message signals, in other words, single tone message signals. For both FM and phase modulation, we can represent, in the case of a single tone, the modulated waveform as some carrier amplitude multiplied by a sinusoid. The sinusoid has 2 pi FCT coming from the carrier, the original carrier, and then a time varying phase component coming from the message. Right? Now, this is a highly nonlinear operation, as we discussed last time, and determining its spectral content is not trivial, even for the single tone case. All right, so we will make use of the low pass equivalent of this signal, which is a high pass signal. We call this a high pass or a band pass, actually, band pass signal, because it is essentially located around FC. Okay, and typically FM here will be much smaller than FC. So we will refer to it as a low pass component. And this FC makes the overall signal a band pass signal. But for band pass signals that are translated by a frequency FC, we heavily make use of this representation where we write the real valued signal as the real part of some complex signal translated to FC. And you've seen this representation in previous courses. Because with this representation, we have the flexibility that if someone gives us a different carrier frequency, this will not affect this part, which is the which is called the complex envelope. Okay, so this complex envelope is not an actual signal that exists in our system, because the actual signal that exists in our system is a real valued signal. Right? It's this U of t. That's the actual signal. However, mathematically, the complex low pass equivalent is going to be convenient to work with. Okay. Now, in this case, we usually the notation for this is goes with a tilde. U tilde is the complex envelope of the bandpass waveform U of t. Okay, and we can represent this as e to the j beta sine 2 pi fm t in this case. So I mean AC in this case is not included in the complex envelope. So maybe when I circle it, I should have circled only this part. Okay, AC is not included. Okay, so the complex envelope is a complex signal. Therefore, its spectrum is not going to be even. It's not going to be symmetric. And when we think of the actual signal, that is a bandpass translation of this signal, you can clearly see this relationship. Shift it and make it symmetric, essentially. And you can do the underlying mathematics. I would strongly suggest as exercise, you write out the relationship between U of f and U tilde of f in frequency domain. Because this we did this in time domain. Now, the nice thing, I mean, I don't know if it's nice, but in our case, it will be the center of our analysis. The complex envelope of our modulated waveform that's coming from the sinusoidal input is periodic with the fundamental frequency FM. Why is it periodic? Well, because it's a complex exponential, so clearly it is periodic, and the fundamental frequency is FM. Therefore, it has a Fourier series expansion, which means we can find Fourier series coefficients in this way, where Tm, the period, is 1 over Fm. So when we write the Fourier integral to find the coefficients, we recognize it as the Bessel function of the first kind. It's called the Bessel function of the first kind. Integral of this exponential e to the j beta times sine x minus nx. It's a function that appeared in the literature before, so people gave it a name. Bessel function of the first kind. In this case, because of this n here, it is the Bessel function of order n. It also has this parameter beta. So order n with parameter beta, not a parameter, maybe arguments beta. All right. So the Fourier series expansion of our complex envelope signal then is in terms of the Bessel function values multiplied by the complex exponentials at multiples of Fm. Any questions so far? No? Okay, so because of this expression, we recognize that somewhat surprisingly, perhaps, our modulated waveform contains infinitely many harmonics. In other words, its spectrum is not band limited. So it has infinitely many harmonics in it. But what are the relative values? What are the relative strengths of these harmonics? We will have to take a look at the Bessel function values. And if we believe that some of the harmonics have very low weights, perhaps we could ignore them and get an effective bandwidth. But let me stress to you, and there was a question last time, if the frequency deviation is going like, so because we computed an instantaneous frequency for FM, for example, Fi of t, which goes like Fc plus delta F, and delta F has a maximum value. How come then is this FM signal, theoretically speaking, infinite bandwidth? Because the cosine, I mean, putting a cosine inside a cosine essentially is a nonlinear operation. Okay, so it is kind of misleading that there's a frequency deviation, yes, but that doesn't mean that the bandwidth is limited to Fc plus delta F. Okay, so for general FM, the spectral analysis is very complicated, but for M of t, which is equal to a sinusoid, we have this analysis in terms of the Bessel functions, which helps us understand the case for general M of t. Now, And let's look at the spectrum a little bit more. First of all, let's keep the signal as general M of t. And you will remember that in FM, the phase is related to the integral of the message. Okay, but when the message is a cosine, the integral is a sine, and we have FM coming here, appearing at the denominator. Now, this thing is the main difference between FM and PM. Because in PM, we're not going to have this FM in the denominator. So that will mean PM is going to have worse bandwidth expansion. The bandwidth expansion of FM is sort of limited because of this division by FM. And we will see later on today that the bandwidth expansion in FM is additive, whereas bandwidth expansion in PM is multiplicative. All right, now let's take a look at this multiplier here that is going to be important to us because we will give it a name. We will call this beta. Okay, it's the multiplier in front of the sinusoid, KF AM over FM. So AM, you know, is the amplitude of the message signal. FM is the frequency of the sinusoidal message in general. FM corresponds to the bandwidth of the modulating signal. And KF is a modulation, something that controls how deep the modulation is. And so this KF AM over FM is going to be important to us in the analysis of these FM waveforms. So now the instantaneous frequency is the derivative of the phase, which is FC plus KF M of t, as we know from before. But now that we have defined beta, we can represent the instantaneous frequency in terms of beta. So the maximum frequency deviation then occurs when the cosine reaches its peak of 1. So the maximum frequency deviation is FM times beta. Remember, this doesn't mean that the spectral content only varies by FM times beta, but it's going to be related. So delta F also is something that we use a lot to characterize FM. As we derived before, in terms of Bessel function values, the signal can be expressed like this. In spectrum domain, we have a sequence of impulses placed at FC plus or minus multiples of FM. Okay. Any questions so far? It appears that we have a typo here. Let me take care of that. We have one AC too many. So let's look at the narrowband case. Last time we did define the narrowband case, and we said, well, turns into an AM signal. Let's take a look. When beta is small, people have shown that this Bessel function can be approximated by, I mean, you could show it by doing a Taylor series expansion, theoretically. Beta to the n over 2 to the n n factorial. And that will imply, since we have this 2 to the n here, if beta is much less than 2, 2 to the n increases much faster than beta to the n, right? If beta is 1 or less, for example, this thing will decay quickly with n. So only the first few terms are significant. Say n equals 0, n equals 1, n equals minus 1. So second or higher order terms will be negligible. And therefore, we can focus on J0, J1, and J minus 1. And notice that the Bessel function has a symmetry property such that Jn and J minus n are either equal or there's a minus 1 multiplication, depending on whether n is even or odd. So for odd terms, the Bessel function, so J1 and J minus 1 are beta over 2 and negative beta over 2. And we can plug these in, this star, the general expansion, the Fourier